Hello everybody, welcome to the second video of Unit 1, an introduction to machine learning. This video is going to cover the types and applications of machine learning. This is presented by Edionics. So let's get started. We're going to talk about three types of learning. The first, supervised learning, in that classification and regression algorithms. We're going to talk about unsupervised learning and how that differs. And then finally, we're going to touch on reinforcement learning. And for all of these different types, we're going to give you some use case scenarios and some examples so that you can understand how and where these algorithms would be used. So let's get started. Again, this is the types and applications of machine learning. All right, so our first type, supervised learning. If you remember, we touched on this briefly in the first video. In supervised learning, you're going to have inputs and outputs, and you're going to have an algorithm that transforms your inputs to your outputs. For supervised learning, the inputs are often called predictors or the independent variable, where the outputs are going to be your responses or dependent variable. So in supervised learning, the machine learning program optimizes the parameters such that the approximation error is minimized. That is, our estimates are as close as possible to the correct values given in the training set. So we want to adjust g of x here in our algorithm so that we minimize our approximation error. So let's take a look at what that would look like. Example 1, we have email spam. And in this scenario, this was a real problem that was solved with machine learning. An automatic spam detector was developed that could filter out spam before clogging the user's mailbox. So to do this, they had a data set of 4,601 email messages, and they classified them into either email or spam. So the outcome class here is just two classes. It's either a genuine email or it's a spam email. And because our output is a class, this is, again, a classification problem. For this problem, not all errors are equal. We want to avoid filtering out good email while letting spam get through is not as desirable, but less serious in its consequences. And again, so this was solved with a classification algorithm and is an example of how a supervised learning algorithm might be used. And again, it's supervised learning, so we have both the inputs and outputs. We start with a database of email messages, which are our inputs, and they are labeled according to email or spam. And we can use that information to train the algorithm. Example 2, handwritten digit recognition. So in this example, we had zip codes that were written on envelopes from the US Postal Service, and they wanted to automatically read these zip codes. However, if you might have noticed, myself included, a lot of people have very bad handwriting, and so sometimes these things are difficult to read. For this problem, you're going to have an output class, 10 output classes actually, 0 to 9. So if you notice, we can have more than 2 output classes. We can have any number of inputs and any number of outputs in these problems. And again, this is a classification problem. Even though it's technically a numerical output here, it's actually just a class because it's the 0 class, 1 class, 2 class, all the way up to 9. For this scenario, we had an input of a 16 by 16 matrix of pixel intensities ranging from 0 to 255 in an 8-bit grayscale image. So on the right here, you see each number. One of these little boxes would be considered the input. So it's a 16 by 16 matrix. That means you have 256 different inputs, where each input is just a pixel intensity at a given location. So this problem has many more output classes and way more inputs as well. So these networks can get pretty big pretty quick depending on the type of problem that you're working on. And again, this is a classification problem. So let's talk a little bit more about what classification algorithms entail. So in classification, you have your inputs, you have your algorithm, and then your output is going to be a class. A lot of these algorithms are going to be defined by the type of output that they produce. So classification, you have a qualitative output, and this is the defining feature of a classification algorithm. So let's look at an example, credit scoring. Not necessarily generating a credit score, but using that credit score to predict in advance whether a customer is going to be a high risk or low risk loaner. So the bank wants to use this to determine how good of a loan they can give you. And it's going to be based on the credit score and past information about the customer, such as demographics, maybe how much money they have in the savings account, their income, stuff like this. So multiple inputs, and your output is going to be a simple class, either high risk or low risk. So let's talk about the features that are going to go into this. First, you're trying to produce a discriminant, and a discriminant is simply a rule that's going to tell you whether or not you're a low risk or high risk customer. So the discriminant is simply a function that separates the examples of different classes. So in this scenario, it's pretty simple because we only have two output classes. And actually, to even further simplify the problem, we're going to pretend that we only have two inputs as well, being income and savings. So we could produce a general rule as such: if income is greater than this value and savings is greater than this second value, then low risk, else high risk. So we wouldn't necessarily need a machine learning algorithm to produce this specific discriminant. However, as soon as you generate more inputs and you have a higher number of output classes, these problems can become very complex, and a simple discriminant is not going to necessarily work, or it's not going to be obvious to you or me. And in those scenarios, we would use a machine learning algorithm to actually form that discriminant. And then once we have that discriminant, we can move on to prediction. So this is what we want to use the discriminant for. We have a rule that fits the past data, and now we can make correct prediction for novelties or new incoming data that we might have. So this is the bread and butter of the classification algorithm. It's using that discriminant that we formed through training to predict what class new data is going to fall into. And again, this example has been simplified to only include income and savings. And so in this scenario, you can see we have a pretty simple line that's going to separate our low-risk customers from our high-risk customers. Again, this is only in two-dimensional input space. As soon as we have a higher number of inputs, this problem becomes infinitely more complex, and in that scenario, we would need to use a machine learning algorithm to solve it. Some scenarios, you might want to predict probability. So instead of just an output of high risk or low risk, you'd actually want to develop a probability that they would be a high risk. And so we're going to talk a little bit about this later when we get into probability theory. However, it can be designated as such, where the probability of Y, low risk or high risk, and X, given the customer's attributes, is going to be written as such. So probability notation is going to be important moving forward, and it's going to be necessary to have a basic understanding of probability theory, which we will touch on more in the fourth video, where we talk about the essential math competencies for machine learning. Another feature that you can use classification algorithms for is pattern recognition. So in this scenario, you have optical character recognition, face recognition, medical diagnosis, and speech recognition. This list goes on and on. However, this is a main use case for classification algorithms. So let's talk about optical character recognition. When you or I looks at the letter A, we can distinguish pretty easily that it is the letter A. However, we might not be able to describe exactly why we say it's a letter A. There's certain rules. We know what an A should look like. However, everybody's handwriting differs, and it's not always easy to tell. But using context clues, the words around it, how they've written letters in the past, we're usually able to deduce what the person writing the text means. However, that's harder to train a computer to do. However, once we're using a classification algorithm, we can extract features that the machine learning algorithm is going to use to solve these problems. So it's going to learn to recognize patterns. It's going to learn to recognize features of the letter A and the letter B, C, D, all the way on, and use those to make correct predictions on novelties, on new incoming input data when it's faced with new handwriting or new faces or new speech, something of that nature. Another use of classification algorithms is knowledge extraction. And this is learning a rule from data, and this rule here is really the discriminant that we talked about earlier. All of machine learning is really knowledge extraction. However, we're talking about the specific rule that is learned from the past data in this scenario. So as soon as you learn a rule, it allows you to explain the data in a much simpler way. For example, if you had 1,000 flips of a coin and approximately half of them were heads, approximately half of them were tails, it would be much simpler to simply say that 50% of the time you're going to get heads and 50% of the time you're going to get tails than it is to store all that data for the flips and the frequencies of occurrences for heads and tails. And so it's going to benefit the user to develop that discriminant which separates the probability of heads versus the probability of tails. In our example before, we're separating low risk and high risk customers. So this is going to tell us about the properties of low risk customers as well as the properties of high risk customers as well. So the discriminant here is the knowledge that we're extracting, and that can be accomplished using a classification algorithm. Once we have that rule extracted, we can use the classification algorithm for compression. And this is really what I was talking about as well with the flipping of the coin, because storing all of the data, all the heads and the tails and when they occurred, is going to be computationally intensive. It's going to require a lot of memory in our computer, especially when we're getting into larger data sets and stuff like that. However, if we fit a rule for the data, we can explain it simpler, and that is going to be easier to store on our computer. So as a result, classification algorithms can also be used for compression. Classification algorithms can also be used for outlier detection. Again, we have a rule, so now we can see scenarios that don't follow the rule and are really exceptions. And as a result, we can classify them as outliers. So as soon as our algorithm detects something that's not behaving according to the rule, we can classify it as an outlier. And as a result, classification algorithms are used fairly frequently to do outlier detection. And again, outlier detection is going to be based heavily in statistics. So we talked about probability theory. Again, one of those core math competencies is statistics, definitely. All right, now that we've talked about classification algorithms a little bit, let's switch over to regression algorithms. Whereas classification algorithms are designated by their qualitative output, regression algorithms are going to have a quantitative output. So you have your inputs, your algorithm, and what you're producing is going to be a number. So that is the designating feature of a regression algorithm. It's quantitative output. So let's take a look at how this would be used. It could be used for generating a used car price. So in this example, we would have the inputs of car attributes such as the brand, the year, the mileage, all these things. How many past owners, has it been in an accident? You could have any number of inputs, and the output is just going to be a numerical price. So you're not going to have any classes. Instead, one simple quantitative output based on any number of inputs. And so this is really function fitting. This is what this is called in statistics. You could have a function y equals mx plus b. This is, again, a very simple example and could become infinitely more complex depending on the number of inputs that you have. But the output, again, is just going to be a simple price, a numerical output y. And m and b in this scenario are going to be the parameters that we optimize. So in this example, the model is linear, and we have m and b are the parameters that are optimized for the best fit to the training data. In cases where the linear model is too restrictive, we could use, for example, a quadratic function or a higher order polynomial or any other nonlinear function of the input, this time optimizing its parameters for best fit. So we're really doing best fit here, and this can be shown in this simple example where we've only looked at the inputs price and mileage. So again, this is just a two-dimensional input space where we're really just doing a best fit line to explain the data. As soon as we generate more inputs, we have a high number of inputs, this becomes, again, infinitely more complex, and we can't model it in such simple terms. However, we can think about it as simply adjusting the slope and the y-intercept m and b here to best fit the data. As soon as we add more inputs, we're going to have to get a higher order polynomial to explain the data. So let's talk about unsupervised learning. This is a much different scenario than supervised learning and is actually kind of its counterpart, the second half of machine learning. Unsupervised learning is characterized by the lack of output data. We have no labeled responses. For these scenarios, we only have the input data to work with, and we don't necessarily know what we're looking for. However, we do have a goal. We're going to try to find regularities in the input. For unsupervised learning, we're making an assumption that there is a structure to the input space such that certain patterns occur more often than others. And we want to see what generally happens and what does not. So this is when we're trying to extract that knowledge from the data, not necessarily knowing what we're looking for. In statistics, this is called density estimation. We assume that the input space is structured. Again, as a result, certain patterns are going to occur more often than others. And we want to look for these patterns so that we can use them in different scenarios. And we'll talk about some of those scenarios later. In machine learning, this is called clustering. You might have heard of k-means clustering. Clustering comes up a lot and is the primary function of unsupervised learning. And it's really a method for density estimation. Again, we've talked about the different terms used in statistics versus machine learning. This is a scenario where machine learning's started to call density estimation clustering. And the aim is to find clusters or groups of the inputs that naturally separate towards each other. So let's take a look at this image. On the left, we have original unclustered data. And looking at this, you might not be able to make sharp distinctions between where the data occurs, but on the right, it's pretty obvious that we can separate this into 3 clusters of data. At least that's what it looks like when it's color-coded as such. You know, we might be able to tell that there's a grouping of clusters in the bottom right in the left image, or a grouping of data points. On the right, it's pretty obvious that that is the red cluster, whereas the blue and the green can also be differentiated as well. So this is a clustering that would be done with machine learning algorithms. And again, this is just in 2-dimensional input space. As soon as you have a higher number of inputs, clustering these data points is not conceptually easy when it doesn't fit into a 2- or 3-dimensional space. So let's talk about an example. We could use this to look at customer data, and it would provide the company with natural groupings of its customers. In the business world, this is called customer segmentation. So our customer data contains demographic info, and we're also going to have past transactions by all of those customers. And then we can use that information to decide strategies to target specific groups or tailor our advertising to those groups. For example, maybe Jack in the Box learns that they have a large group of customers who get the munchies late at night and come in past 10 o'clock. As a result, they're going to start targeting those groups of individuals, whereas maybe an investment company or a retirement company learns they have a large demographic of retired individuals and they're going to target them. So we want to learn more about the natural groupings of customers so that we can use advertising and strategies to target them better. Another example would be document clustering. And this is where we're going to try to group similar documents. So a document would be represented as a bag of words in this scenario. We're probably going to remove non-informative words such as of, the, a, and focus on more of the nouns and verbs that would occur. And once we have that bag of words, that bag of words would be used as an n-dimensional input. It would be a vector whose element I is 1 if word I appears in the document or not. And then we can cluster these documents into similar types of documents. So a news company might use document clustering to sort news articles that relate to sports versus news articles that relate to travel or maybe politics. Each of those documents is going to have natural groupings. The the words that occur in a political news piece are going to be much different than the words that occur in a sports piece. As a result, they can be separated using an unsupervised learning algorithm of this type. So that's unsupervised learning. Let's jump over to reinforcement learning. Reinforcement learning doesn't really fall into supervised or unsupervised learning. Sometimes it's called semi-supervised learning or Q learning. In reinforcement learning, we're going to have our observations, which are our inputs, our algorithm, and then as a result, we're going to have a sequence of actions. So the output here isn't a class, it isn't numerical, but it's going to be a combination of actions that allow us to reach our goal. So each individual action isn't going to be important, but the policy, the sequence of correct actions to reach the goal is going to be what is essential. So reinforcement learning algorithms have a lot of really interesting use cases. Example one, game playing. A move is good if it's part of a good game playing policy. However, each individual move isn't as important. What's important is winning the game. Games are really easy to describe. They have a set of rules that can be defined. Thinking of chess, it's pretty easy to program the rules of chess, but it's much more difficult to actually play. So reinforcement learning and game playing specifically is very important to AI and machine learning. And some examples of this are with the games chess or Go. AI algorithms or machine learning algorithms, they're really reinforcement learning algorithms, have been used to master both chess and Go. And so I said I wanted to include articles about current advancements. This article is about a year old, but it's definitely worth a read. In this article, which appeared in Nature, an international weekly journal of science, which is very well regarded, the Google AI algorithm actually beat several professionals at the game of Go. The game of Go has more possible games than atoms in the observable universe. So for an algorithm to be able to play this game and play it effectively is very impressive. And this is very important research to machine learning and AI in general. And again, of course, it's Google who's doing this. Google has all of the data, and so they are definitely on the forefront of machine learning. Another example of reinforcement learning would be robot navigation. So a robot can move in one of any number of directions. How each individual move isn't as important as long as it meets its final goal. So it'll learn the correct sequence of actions to reach the goal state from the initial state, and reaching that goal state is what's important. We're certainly going to try to optimize our route to the goal state. We want to reach the goal state as efficiently as we possibly can. We don't want to have a self-driving car that's bouncing off the rails on the road as it drives down the street. We want to get there efficiently and safely. So we're going to try to optimize that route, but each individual move, again, isn't as important as making it to the goal state. So we're going to have a final project at the end of this class, and in this final project, we're going to take a look at the OpenAI Gym. So the OpenAI Gym is an environment that has been used to train reinforcement learning algorithms in to play like Atari games or other similar tasks such as that. So the scenario we're going to look at is the cart pole, where we're actually balancing a pole on a cart. So this pole has a tendency to fall due to gravity. However, our reinforcement learning algorithm is going to learn to actually balance the pole on top of it. So this is a deep learning reinforcement algorithm, and we're going to talk more about deep learning and neural networks in Unit 4. We're going to talk about reinforcement learning more in depth in Unit 3 when we talk about unsupervised learning. So this will be a great program to take a look at so that we can understand these topics better. And this is going to be programmed in Python using TensorFlow, which is a machine learning package that was developed by Google again. And so this will be a really fun, challenging problem for us to do that will help reinforce some of these concepts that we're talking about in this class. Okay, so that concludes our second video, the types and applications of machine learning algorithms. Let's do a quick summary. We have supervised learning where we have inputs and outputs. In supervised learning, we have classification algorithms which have a qualitative output, and we also have regression algorithms which have a quantitative output. In unsupervised learning, we have no labeled data. We only have the input data, and we're looking for natural groupings or clusters of the data so that we can use that knowledge for different purposes like targeted advertising. And then finally, we have reinforcement learning, which is sometimes called semi-supervised learning, and we are trying to generate a sequence of actions to reach a goal state. So we have observations, we feed those into our algorithm, we get a sequence of actions out. Thanks for listening. Our next video is going to be on the differences between artificial intelligence and machine learning, as well as the similarities, where there's overlap and where there's misunderstandings. Thanks for listening.